The first speaker is Kenta Oishi, and he will talk on global well-posedness and decay for a free boundary problem of the Navier-Stokes equation in unbounded domains.
Thank you. Thank you for your kind introduction. And first of all, we would like to thank to the organizer for giving me the opportunity to talk in this conference. Today, we will discuss about the global well-posedness and decay for a free boundary problem of the Navier-Stokes equation. Yes, this is my title, and this is joint work with Professor Shibata from Waseda University. So this is my contents of my talk. First, we would like to introduce our problem and then give the statement of the main theorem, which is on global well-posedness and decay in general domains. Then we see the sketch of the proof, and finally we discuss about the case in half space. First, we introduce our problem. We consider a free boundary problem for the Navier-Stokes equation. The fluid is viscous and incompressible one, and we do not take surface tension into account. And then the equation is given by this. The first equation is derived from the conservation of momentum, and second, it's derived from conservation of divergence. The third one is boundary condition for the free boundary problem, and fourth is kinetic condition, which means omega t coincides with the domain of fluid. So this situation doesn't occur. And finally, this equation means the initial condition. Unknowns are domain omega t, the evolution speed of the boundary Vn, velocity, and pressure. Knowns are initial domain omega 0, which I write omega for simplicity, and initial velocity v0. Also, as a notation, SVP is a status tensor, which is given by this. And DV stands for double deformation tensor, which is given by this. And mu is a viscosity coefficient, and I means identity matrix. As a non-result on global well-posedness without surface tension, in L2 framework, Solnikov proves the result in bounded domain, and Tani and Tanaka in asymptotically flat layer, and so on. In LP framework, Solnikov gets the result in bounded domain, and LP in time, LP in space framework, Shibata proves the result in bounded domain, Saito in flat layer, Shibata in exterior domain. Also, on the half space, which we consider later, although with surface tension, Saito and Shibata proves the result LP in time, LP in space framework. In these two results, it is used that zero is the servant of Stokes operator. As for the third result, zero is continuous spectrum, but make use of, as the author, make use of non-compactness of the boundary. However, we find that the non-compactness of the boundary is not needed to get global well-posedness. This is my main result. So we obtain as a main result the global well-posedness and the decay in general domain, assuming that the unique solvability of a weak decay problem. And this implies, sorry, I forgot to fix, sorry. Due to average Soa and Shibata, this implies maximal regularity. Also, we assume LQLR estimate for the Stokes semigroup. Although in this result, we can't take n equals 3, but in half space, we can take n equals 3. This is our main result. So let me give a statement of the main result. This is the free boundary problem we consider. Since the domain is time dependent, in order to reduce this problem to one in a fixed domain, we formulate this problem in Lagrange coordinate. So x is Euler coordinate and y is Lagrange coordinate. And by using this transformation, we set u and p as velocity and the pressure in Lagrange coordinate. Then we get a quasi-linear problem in fixed domain. This. Here, if u, gu for the font of gu and hu is nonlinearity, which is given in next slide. Also, the kinetic condition this is automatically satisfied when we use this transformation. Okay, we give the nonlinearities. Nonlinearities are given by this, especially, sorry, V1 to V6 is, yes, and W some polynomials with Vi0 equals 0. So the constant sum is 0. Especially the nonlinearity includes the second derivative, so highest derivative of solution. So the system is quasi-linear problem. As a method to get decay of the solution, we combine the maximal LP-LQ linearity for the shifted problem. So I shift the resolvent by adding lambda 1 u1 like that to the left hand side. And so with an estimate for the Stokes semigroup to compensate the difference between the solution of original problem and shifted problem. Yes, so to get this two property, we assume some assumptions. First assumption is unique solvability of a weak problem. As a notation, we define W hat 1 to 0 as the set of all functions such that first derivative is in LQ and the boundary, the value on the boundary is 0. Then this is assumption 1. For any f, there exists a unique solution theta of the weak derivative problem of Poisson equation, and it possesses the estimate this. So this term is estimated by this term. This assumption is needed to eliminate theta term p from the Stokes equation and to define the Stokes semigroup this. Also, we assume this to obtain the maximal regularity due to average Terasawa and Shibata. So let me give the statement of the maximal AP-LP regularity. So we can start shifted problem. So I added lambda 1 u to the left hand side, where lambda 1 is large real number to get the decay of the solution. As a notation, to state the to give the statement, we define W hat minus 1q, which is defined as real of W hat 1q prime 0. Also, so this is type h 1 over 2p as the set of all LP functions such that the time derivative with order 1 over 2 is also in LP. Here, this derivative is defined by using the Laplace operator. No, Laplace transform, sorry. Yeah, Laplace transform is defined as by using Fourier transform as inverse Laplace transform is defined as inverse Fourier transform, but I skipped the detail. Now, let me give the statement of the maximal regularity, which is roughly the estimate for Stokes equation, which controls the highest derivative of solution. So take PQ in this and P as a weight. There exists lambda 1 such that for any data in this class and with appropriate compatibility conditions, the shifted problem admits a unique solution with P with this class. Moreover, the solution satisfies this estimate. So the W1PLQ norm and LPW2Q norm of weighted U and sorry, this is typo. LPLQ norm of weighted weight times the partial derivative of P is estimated by this. So this is the statement of the Maximal inequality. And as assumption 2, we assume LQLR estimate. Let AQ be the Stokes operator on the solenoidal space JQ. Then, under assumption 1, AQ generates the analytic semigroup this. Now, let me give the statement of assumption 2. Take QR and M satisfying this. Then, the LQLR estimate for time derivative and itself or space derivative with decay sigma 2QR or sigma MQR holds, where sigma MQR is given in the statement of main theorem. So we consider the general case. This estimate is obtained in half space and whole space and half space when the decay is same for heat equation this. Also, in exterior domain, it is obtained when the decay is same for m equals 0 and 1, and the decay is the minimum of that for heat equation and n over 2q for m equals 2. We consider the we consider sigma MQR as a general decay, but especially we consider this exterior domain case. Now, let me give the statement of main theorem. First slide is about the exponent and decay for LQLR estimate. Let P Q0, Q2, and weight B. B is the weight appeared in the statement of maximal visibility. Satisfying this. Let omega be a uniform C11 domain and assume assumption 1 and 2, which is the unique solvability of a weak dirichlet problem and LQLR estimate with this condition for the decay. But I will skip the detail. However, when the exterior domain case, if the decay is same as for exterior domain, the conditions are equivalent to this. Unfortunately, this implies because Q2 is larger than 1, and so we can't take n as 3. However, we obtain the result for if n is larger or equal to 4. The next slide is about the global well-posedness and decay. In such a exponent and decay for LQLR estimates, there exists epsilon such that for any initial velocity is smallness this and compatibility conditions this, the token one, which is Lagrange formulation of the free boundary problem, admits unique solutions in this class, possessing the estimate is where here the bracket of U in the left-hand side is given in next slide. Moreover, the solution has a decay property this. The decay is almost same as LQLR estimate. However, it should be smaller or equal to B, the weight B. So we take minimum here. So let me explain the norm bracket of U. The bracket of U is given by this, which is something like terms of weighted LP to the LP norm with weight. So about this, if we focus on this term, LP norm, LP to the norm of weight with power p to the q to the times second derivative of U or time derivative of U. Here the weight p to pq about this 2 is from this, and p to the and p to the is from this. So the being p to the q to the is LP to the LQ to the norm of mth derivative with weight. We take the m p to the q to the as this. It is natural in O by B in view of the decay this. So I mean it is natural to take Bm as the decay for LQLR estimate or the solution with minus 1 over p theta minus theta to get the summability for LP norm in time, and take minimum with B. Also, I2, I1, I0, which are range of P theta and Q theta, is given by this, but I skip the detail. So this is my main result. Now, let me compare with the case in exterior domain. In exterior domain, the global well-posedness and the decay is obtained for also n equals 3 by using the transformation this. So unlike in our case, unlike in our case, the cutoff function kappa y is multiplied in here. Then the nonlinearities become like this. The advantage to use this transformation is nonlinear terms have compact support. Then we can estimate this by something like L infinity norm, and it is advantage to when we apply LQLR estimate. Then by taking this advantage in x to n equals 3 is allowed. But as a disadvantage, the lower derivative term appears here. So in general domain, we can't use this transformation. So we use, sorry, I forgot to say that if lower derivative term appears, we can't use this decay. So in general domain, we don't use, in general domain, we can't use this transformation, but we use this decay. So let me see the sketch of the proof. The strategy is to prolong the local solution and proofs a priori estimate this. As a step 1, we estimate the solution UP to the linearized problem and prove this. Here, we prove the decay of the solution U and then get this estimate. As a step 2, we estimate the nonlinear term and get this. Here, NFGGH is the norm of data or nonlinearity, which is given by this. I skip the detail, but the essential term is this lower derivative term. In view of the reason, we can't take n equals 3. But I'll see this later. Okay, step 1, we will see about the step 1, which is the estimate of the linear problem. So linearized problem, sorry. Which is this Stokes equation. We decompose this equation to these 3 systems. First system is almost same as the original one, but I add lambda 1 u1 to the left-hand side. By this, we get the decay enough to the position u1, because we can shift the reservant by this term. However, to compensate it, we have to add the same term to right-hand side. So we add it to the right-hand side of second system. Also, we repeat this procedure to the second system and third system. So I mean, add this term to the left-hand side of second system and right-hand side to the right-hand side of the third system. We repeated this procedure to get this property. The right-hand side belongs to the domain of AQ, so Stokes operator. Now, the estimate or decay of U1 and U2 is obtained by the maximal visibility, so we focus on the estimate of U3. What we should show is this estimate, where the bracket of U3 in the left-hand side is given in the statement of the main theorem, and this. Now, we write U3 as by using the semigroup as this, and decompose the interval of integral as this. Here, we have difficulty when we estimate this second derivative, and also we this is a decay is sorry. We can see the decay is we can see the decay is same as that for LKL estimate when we estimate this. So first, we talk about the difficulty on this, and next we see the estimate of this. First, about difficulty. Difficulty is singularity on S equal T. In fact, consider the estimate of this. We write you see by using semigroup. So principle of the geometry principle, and by using the pointwise estimate of semigroup, we have this. Then, because the power is -1, we have singularity on S equal T. However, the singularity disappears when U2 belongs to domain of Stokes equation, no, Stokes operator. To see this, consider the estimate of this. So we begin with this formulate. Using the equivalence of norm WTQ and domain of Stokes operator, first we use this property to get this. Then you get this. And because U2 belongs to the domain, we can extend this to term. Then use the pointwise estimate of semigroup and this property, we get this, which means that singularity disappears. This is the idea to overcome this difficulty. And next, we will see that the decay is same as that for LQLR estimate. Remember that we decompose the solution as U1 plus U2 plus U3 and decompose the solution formula of U3 as this and this and this. Then we focus on the now we are focusing on this integral. So we estimate this. Now use the pointwise estimate. No, use the LQLR estimate here. Then you get this. And this is the LQLR, the decay for LQLR estimate we assumed. Then, since we know U2 decays fast enough, we multiply this term to here and inverse to here to get the solvability of A with respect to S. Also, we estimate this term by this term using this relation, and this is decay. Then, by delta inequality to this implies this. Then, by this property, this is constant, and we found that this is decay. So the decay of solution is same as that for LQLR estimate. Then, by using this, so the decay for solution and solution, the decay for solution minus p theta 1 over p theta minus theta to get the, sorry, yes, I mean, this part is to get the AP theta, to get the solvability of AP theta. Then, taking the AP theta norm, we get the desired estimate. And this is the estimate of this. About this term and this term is similar. Is similar estimates, so I'll skip it. Then we conclude the step 1. We have said that U equals U1, U2, the sum of U1, U2, U3, and P as P1 plus P2 plus P3. And set to be U is weighted norm of the maximal regularity class. Also, we have set the bracket of U as this, which is given in the statement of the main theorem. Then we have seen that the estimate of U3 is obtained by this property. Also, about U1 and U2, we estimate this by this by B, and the sublet embedding implies, and then use sublet embedding. Then we get the estimate of UI. Yeah, we used this property. Then maximal regularity concludes the desired estimate. So the step 1 is okay. Next, sorry. At the step 2, the estimate of the estimate nonlinear term. Here we focus on the case that decay for the educator estimate is same as that for exterior domain. What we prove is the norm of nonlinearities is estimated by this. So in view of the decay we obtained in step 1, the slowest decay term will be this. We can expect that in view of this term decays slower than this term. So with order 1, with order t with power 1. And the other term decay not slower so much. So this is slowest decay term, and we consider the estimate of this. So I mean, this is essential part. So next, essential parts to estimate. Yeah, GU is given by this, where V is polynomial with z equals 0. Since the integral is bounded, so regarded as constant, we only have to consider this norm. So we will see the estimate of this. So we estimate this by the Heritage inequality. If we set Q3 and Q4 as this, we get this estimate. And apply the Heritage inequality to here, we get this. Then the desired estimate, this is obtained when this and this. The first condition is needed to estimate this by a constant. Also, the by step 1, the power of weight should be smaller than this. So we need this condition. And then, so write down these two conditions as this. Then, combining these two conditions, we get this. Because this and this cancel with this. So we will add this to infinity. So then this and this three terms cancels, and this term is cancelled, and this and this and this term is cancelled. Then we get this. Also, this implies this. Then we found that we can't take n equals 3. However, if we assume this condition, we get the desired estimate. We can prove this. Also, okay, never mind. Finally, we see the case in half space. The main theorem is stated as follows. Let n be this, and p, q0, q2, and weight b satisfies this. Yes, assume this. Then there is the global well-posedness and decay, same as in general domain, is obtained. But previously, there exists epsilon such that for any initial velocity with smallness and compatibility conditions, the problem 1, which is the Lagrange formulation of the free boundary problem, admits unique solutions in this class. So in the same class, using the same estimate and same decay. So this is our second main result. Let's see the sketch of the proof. First of all, the assumptions 1 and 2, which is the unique solvability of a weak problem and LQLR estimates are obtained by Shibata and Schmidt and routine work. So we have to check that we can take n equals 3 in the theorem. The difficult part is the slowest decay term, which is given by this. And the strategy to overcome this difficulty is reduction of the Stokes equation to the case g equals 0. So that this term doesn't appear. So for this, yes, sorry. In order to reduce to the case t equals 0, we use this lemma 1, which is on solvability of divergence equation. Let Q be in here. Then there exists an operator K0 such that K0 is solution operator of the divergence equation, and also satisfy this inequality as a good estimate. That is, the second derivative of solution is estimated by first derivative of data, and first derivative of solution is estimated by data itself, and solution itself is estimated by W hat minus 1Q. So this is lemma. And in the next slide, we see that after reduction, the slowest decay term doesn't appear. So consider this Stokes equation and set U equal K0G plus and V. K0G plus V. Here, K0G is the solution of the divergence equation. Then Vp obeys its Stokes equation with G equals 0. Then, if we repeat the proof of the Theorem 1, V is estimated by this part, and also K2G is estimated by this. So new term appears, but this is harmless, which I skip the detail, but this is harmless. And we focus on this part. So using this definition, this term is estimated by this and this and this. Oh, sorry. I forgot to write this. So the font of G is this G. This G. I'm sorry. So yes, I'm estimating this part. So this part is estimated by these three terms, and also this term is estimated by, so using this term, and from here, this term. So we want to emphasize that this slowest decay term doesn't appear. Then we get the desired a priori estimate, and so we can take n equals 3 in the half space. That's all. Thank you so much. Thank you for your kind attention.
Yeah, thank you for your clear talk. So we have time for some questions. Yeah, the first question is maybe Helmut Havels.
Yeah. First of all, thank you very much for the nice talk. I'm Helmut Abels from Regensburg. So in your second theorem, you consider the half space, or let's say a free boundary layer problem close to the half space. My question is now, can you also treat the case where the domain is only asymptotically a half space? Let's say you have a big local perturbation and something which converges at infinity to a half space.
I don't expect the theorem holds because firstly, the resolvent estimate is not obtained for the part of the case, and also the reduction of this is not
but it is more a problem that the results are not available, the analytic results for linearized systems are not available, or is that a fundamental problem, do you think?
sorry, please.
You said, do you expect a fundamental new problem when you have a perturbed half space? Or is it more a technical problem that some results are not available so far?
Sorry, I don't have an idea.
So, okay, but at which points is it essential that you really have a half space?
What point?
Yeah.
Sorry, one more, please.
Okay, then thank you. May I ask a second question?
Sorry.
Yeah, of course.
Did you think about a situation where the boundary, part of boundary, you have a free boundary, and a part you have Dirichlet boundary?
I'm checking it now.
Okay. Okay. Then I would expect that some things are easier if there are some part you have Dirichlet boundary, since, for instance, rigid motions are no longer in the kernel of the operator.
Yeah. Okay. Thank you.
Thank you.
Yes, I agree.
Yeah. Jürgen has another question.
Yeah, hi. Yes, Jürgen Saul from Düsseldorf. My question is somehow related to Helmut's question. So what you need is you need the solvability of this Dirichlet problem and the LP-LQ estimates for Stokes. Yeah, this is what you need. You need domains such that this is available, right? So could you give maybe some examples what kind of domains you can cover with your approach? Except, I mean, you're away from compact boundary, but what kinds of domains concretely can you cover? Can you, for example, cover something like the domain of Bokovsky and Maslenikova, a non-Helmholtz domain, something like this?
So we can cover the domain, for example, half space, but sorry, this half space on exterior domain and first layer is lower bound is fixed boundary and bounded domain, and half space is for kind of domain, I think.
And something like a smoothed out cone, for example?
I don't know about that. So I don't know. So the recipient estimate is the problem is the recipient estimate is explained or not. So I don't expect the result for cone now.
You don't know?
Yes, I don't know.
Okay, thank you.
May I? My name is Shibata.
Yes.
May I answer something? Because
Thank you. Thank you so much.
co-workers with Oishi. Yeah, thank you very much. Several interesting questions. And for example, Professor Hours, yeah, no, I think actually the point is that how to estimate the, so his notation is capital G. It's come from integration of nabla u times u. It's come from the divergence conditions. Then, so for example, half space case is that you can eliminate these terms by some of the substitutions. So he says that the case of G, therefore this difficult terms disappears. And also the domain is, boundary is compact, then some kind of cutoff techniques. Okay, so, all the estimate is reduced to the Q, and the Q is greater than N. Therefore, the decay properties near the compact, boundary is very good. Therefore, three-dimensional cases can be applied. But non-compact boundary, I think maybe you can prove that LP-LQ decay estimate the aperture domain or some perturbation from the half space or something like that. But I'm not so sure that, for example, the Jorgen said that some what to say cone domain, and the cone is, for example, the cone angle is greater than pi. Maybe is that no, sorry, less than pi. Excuse me, less than pi. Then maybe you don't need the boundary condition, or boundary condition very nice. Therefore, maybe you will be able to get a similar decay rate than the whole space. But cone domain, the angle is greater than pi. Then it's really, you need the analysis for unbounded domain. Therefore, I think that in general, decay property is not enough to prove that the global well-posedness. Therefore, maybe dimension n, and the assumption that the dimension is greater than or equal to 4 may be necessary. But it's also the question from Professor Abels. It's also very interesting that the perturbed half space, like perturbed half space. Yeah, I have no answer to now, but maybe it's possible to consider solve the problem in n equals 3 case. I think that maybe. But sorry, it's not sure. I mean, just I'm thinking that it's a good problem for us. Physically, also very interesting problem. Okay, very nice problem. Thank you. Okay.
Yeah, thank you very much for the additional explanations. So is there still a question by Jürgen, I think?
Sorry, no.
Yes.
Okay. A question by Kishi, maybe.
Hello, this is Keiichi Watanabe from Waseda University. Thank you
Yes.
for your talk. And I have one short question. Concerning for your first result,
Yeah.
Clearly, if the domain is bounded, then your result holds. Is that correct?
Ah,
And so, because if the domain is bounded, there exists non-trivial stationary solution. So that, for example, Shibata and Shimizu introduce some orthogonal condition, like the initial velocity is orthogonal to a rigid space. Don't you need this kind of condition if the domain is bounded?
so I think the assumption to LQLR estimate should be obtained in not JQ, but no, but this space for bounded domain. So we need.
So you mean that if the domain is bounded, then a further assumption is required?
Yeah, like that. So
okay.
You need to change the underlying space.
Okay, thank you.
Yeah, thank you. Maybe one last question. So if you consider surface tension, this usually has some smoothing effect. What do you think? Will your results still hold if you include surface tension?
I'm thinking about it, but yeah. Sorry, I'm not sure, but we can. I think we can obtain the similar result, but the decay might change from this because an in-half space which is obtained in Taito and Shibata, the decay is changed. So
I see.
Yeah, decay might change, but I think the global well-posedness can be obtained.
Oh, yeah, thank you.
But maybe a comment to that, but I would expect that in the case of surface tension next to your domain, one has to assume that the boundary is close to a surface, to a sphere. Since in the case of surface tension, let's say the boundary will become a surface of constant mean curvature, which is not the case without surface tension. So in some sense, I would expect you have to be either flat or close to a flat boundary or a sphere or another surface with constant mean curvature. So I think surface tension will really introduce a new effect.
State, so to say.
May I answer? Shibata answer.
Thank you.
Okay. Yes, I already Oishi said that Saito, Professor Saito and myself work on half space with surface tension. I think this case is, in some sense, we know that the LP, LQ nice decay rate and also maximal regularity. Therefore, the method is the same as Oishi explained. But point is that how to get a nice decay rate. And then I think maybe the part of half space is possible. But if you consider some layer, and even the bottom is the Dirichlet condition, layer case, I don't know. I just want to ask Professor Abels, that you already have some decay rate of this kind of layer case or the part of the layers?
To be honest, I didn't study, to be honest.
Oh, sorry?
Sorry, I didn't study strong solutions with surface tensions. So somehow into the layer case, I left somehow after my thesis.
It's very, I think, yes, I think exterior domain and then the surface tension is, I don't know, it is not so nice problem. Maybe it is ball, it breaks, or I don't know, but half space or the layer is a very natural problem to consider the surface tension, like ocean problem. Therefore, it's quite interesting for me. And then maybe method is just I hope that the Oishi presented method is the works. So pointed at how to get a nice LP LQ type decay estimate even for the surface tension. This is my answer.
Yeah, okay, thank you. Yeah, so if there are no further questions, then let's thank the speaker again.